It is a real honor today to introduce Mark Krumholz. Mark Krumholz is a widely known expert on theoretical studies, mostly of the interstellar medium, star formation, feedback in galaxies down to individual stars across cosmic history. And he did his PhD at UC Berkeley in 2005, moved on to Princeton on a Hubble Fellowship. Since 2008, he was a faculty member at UC Santa Cruz, where he also held the Sloan Fellowship. And in 2015, he moved to ANU in Canberra, Australia, as a full professor. And he is at the moment actually in Heidelberg, just arrived last week, I think, or 10 days ago.
Something like that.
On a Humboldt Fellowship as a sabbatical visitor, sabbatical professor here for the next 6 months. So this is a wonderful opportunity to be introduced, undoubtedly even more than you already know, to his wide array of work, and also to maybe set up plans for meeting him during the next couple of months. So with that, please let's give Mark a very warm welcome and for his talk on the origin of turbulence in the interstellar medium.
Thank you very much for that introduction. I'm very glad to be here, not least because here is not currently on fire, which is more than I can say of the place where I normally live. So, you can actually breathe the air here and not see it, so thumbs up. All right, so I am going to try and tell you something of what my collaborators and I have understood over the last 5-ish years about where turbulence in the interstellar medium comes from. And I'll clarify a bit more about what I mean by that, what I mean by turbulence in the interstellar medium, and here's the plan for the talk. All right, so I'm going to start with just the observations. What is it we're trying to explain? All right, we'll talk about the observations of kinematics of interstellar gas, what do we actually see, and we'll talk about the gas content and the fuel for star formation in galaxies. All right, and then I will spend the bulk of the talk going through models for trying to make sense of this, trying to make sense of what we observe about the kinematics of gas in galaxies. And I'll talk about a model where it's mostly due to stellar feedback, a model where it's mostly due to gravity, and then I will propose a model where you can get the best of both worlds and put these two things together, and I think explain a lot of the data. I will then, of course, no theory is perfect, many are the opposite of that, go to a place where that theory utterly breaks down and you need to invoke entirely different mechanisms to explain the turbulence in the interstellar medium, and that's the central molecular zone of the Milky Way. And then we will end with the inevitable and unavoidable conclusions and future prospects for those of you who fall asleep during the talk. All right, so here's where we'll begin. I'll give you a moment to read that. Yeah, did I mention that some astronomers went into astronomy because they grew up with their backyard telescope and they gazed out at the stars? I grew up 5 minutes from Manhattan. The night sky for me was no stars, it was buildings. I first saw the Milky Way with my own eyes when I was a PhD student. So there you go. All right, so here's sort of the basic observation, not made by me, obviously, that we would like to understand, which is that if you look at the interstellar gas in nearby disk galaxies, what you find is that it is sort of transonic or supersonic. The gas is moving around of order the sound speed. All right, and this is illustrated here in a couple of different observations. I think some done by people who are, if not in the room, their advisors are in the room. All right, so this is just the velocity dispersion as a function of gas surface density in nearby dwarfs and nearby spirals. And what you see is that it's typically 5-10 kilometers a second. All right, here is breaking it down by components. All right, so H1 is the neutral hydrogen in the galaxy. CO is tracing the molecular gas. All right, and what you see is similar velocity dispersions of about 10 kilometers a second. All right, so this is sort of observation number one. If you go to any local galaxy, normal local spiral galaxy or dwarf galaxy, and you measure what's the velocity dispersion of the neutral interstellar gas in that galaxy, you will get a number that's of about 10 kilometers a second. All right, now, for comparison, in the warm atomic medium of the Milky Way and similar galaxies, the sound speed is of order 5 kilometers a second. So this is sort of transonic, Mach number of 1, maybe 2, with respect to the warm gas. It's, of course, significantly higher with respect to the CO, which is the cold gas. I don't want to dwell on that too much. The point is you get a number of order 10 kilometers a second. All right, and this seems to be close to universal. There's very, very little variation in the local universe. All right, but if you go to more distant galaxies, high redshift galaxies, you find much, much higher velocity dispersions. All right, and this is illustrated here in a couple of plots. So on the left, I have here some H alpha data from Kresge et al., and just focus on the panel that's not shaded. This is the estimated velocity dispersion. All right, and if you look at the scale bar there, you'll see numbers that are more like many tens of kilometers a second. All right, this is a summary plot from Emily Wisniewski, just putting together surveys of typical velocity dispersions as a function of the redshift of the sample. All right, and here we see the local universe down at redshift 0, typically about 10 kilometers a second. And as you go back in time, things increase to tens of kilometers a second. You go back far enough, you get, 50, 80 kilometers a second. Now, these points should be taken with a considerable grain of salt. There are large error bars on them. Nonetheless, you can robustly rule out the possibility that galaxies at redshift 2 or 3 have velocity dispersions comparable to those that you see in local galaxies. There's no way you can make the data fit that. All right, so clearly something is happening over cosmic time. Galaxies have become less turbulent from redshift 2 or 3 to today. All right, now, while they've become less turbulent, other things haven't changed, and here's a very important one. The degree of gravitational stability or lack thereof has not changed. So that's illustrated here. So on the left, we have data on local galaxies from Martin and Kennicott. So the x-axis is the radius of the is radius in a normalized sense, and the y-axis is the gas surface density normalized to the gas surface density that would be required to make the galaxy marginally gravitationally unstable. All right, and what I mean by that is you can imagine taking a disk of gas which is rotating. If you have the competing forces of gravity, which wants to make the gas clump up, and shear, which wants to tear clumps apart, and pressure, which of course wants to push clumps apart. As you raise the amount of gas in the galaxy, as you raise the surface density, gravity becomes stronger compared to shear and pressure, and eventually you get enough gas that gravity wins. There's a critical surface density there, and that's what this mu crit is. And what you see is that these galaxies are, with significant scatter, all clustering around gas divided by critical value is around 1. All right, this is at redshift 0. You can also do this sort of analysis at redshift 2. And that's in this plot from Genzel et al. So this Q parameter is basically just this mu gas over mu crit, modulo a factor of order unity. And again, you see typically numbers that are, within a factor of 2 of unity. All right, and the error bars here are at least a factor of 2, so you should not view this as, significantly different than unity. All right, so even though the velocity dispersion, which is a component here because that affects the dynamical pressure, is vastly different here than here. Here it's 10 kilometers a second, here it's more like 50 or 60. That is compensated for by a change in the amount of gas such that Q stays about the same. All right, so that's a commonality in the turbulence of low and high redshift galaxies. Here's another one. They fall on a common relationship between star formation rate and velocity dispersion. Now, this is, I am the first to admit, as the one who made this plot, a horrible plot. All right, and it's a horrible plot because if I showed you the error bars here, there'd be nothing but a field of error bars. Nonetheless, there are trends that can be discerned. All right, so just to orient you, x-axis here is galaxy star formation rate, y-axis is gas velocity dispersion. All right, all the local galaxies, things at redshift 0, are shown in shades of blue and purple. And that's mostly what you see down here. All the high redshift galaxies are shown in shades of yellow and orange, and that's mostly what you see up here. All right, now you could say that these are two different populations, and to a large extent they are, but that's largely an observational illusion. And what I mean by that is there probably are high redshift galaxies down here, you just can't see them, they're too dim. On the other hand, you can find local galaxies, things that are blue and purple, with higher than average star formation rates. You see there's this smattering of, say, triangles, circles, etc., that are blue and purple here. And what I want you to notice is that they land on basically the same place as the high redshift galaxies. All right, so that is, high redshift and low redshift galaxies seem to fall on a similar relationship between star formation rate and amount of turbulence in the interstellar medium. All right, if you go and find an unusual low redshift galaxy that has a star formation rate of 10 or 20 solar masses per year, it will have a velocity dispersion comparable to that of a high redshift galaxy with that star formation rate. They're rare in the local universe, but they exist and you can go out and find them. And indeed, all these blue points that you're seeing living over here are a sample that was explicitly constructed to look for local analogs to high redshift galaxies. All right, so there's a common relationship here.
Why is there a minimum?
That's an excellent question. We're going to get back to that. I will attempt to explain it. That is a very, very good question. Why does this flatten out and not go all the way to zero? It's not an observational artifact, it's real. All right, so what's going on as we go from low to high redshift? What's the explanation for this? Well, one obvious difference between low and high redshift galaxies that at least drives the evolution along the x-axis, if not necessarily that along the y-axis, is the amount of gas that's present in these galaxies. All right, and so that's what I'm illustrating here. All right, so this is sort of two ways of getting at the history of gas in galaxies from Linda Tacconi's work. All right, so the hard way of doing this is you actually go out and measure the gas directly, and that's what's shown on the right here. All right, so this is a sample of galaxies for which she has measured the molecular gas content at redshift of about 2, and what's plotted on the x-axis is the molecular gas mass divided by molecular gas plus stellar mass, and what you see is that the molecular gas is usually about half the mass in these galaxies. Now, by contrast, in local galaxies, it's generally under 20%. All right, so we've gone from 10 or 20% is the typical gas fraction to 50% at redshift 2 or 3. All right, now that's the hard way, but direct way of doing it. The easier and more indirect way is you can't measure the gas so easily, so you instead measure a proxy for it, which is the specific star formation rate. That is, the star formation rate of the galaxy per unit stellar mass it already has. All right, so that's just telling you how quickly the galaxy is growing. A specific star formation rate of, say, 1 inverse gigayear means this galaxy will double its stellar mass in 1 gigayear. 0.1 means it'll double its stellar mass in 10 gigayears. And what you see here is that there's a very clear trend in specific star formation rate with redshift. As you go from low redshift to high redshift, the specific star formation rates are going way up. And this is at least plausibly because these galaxies are more gas-rich than these. All right, so that's an obvious candidate for what's driving that evolutionary sequence. All right, now you can, in fact, look more precisely at how that evolution is happening. You can look in a spatially resolved way. All right, so again, I'm showing you on the left local and on the right high redshift. All right, so on the left we have just a direct measurement of the gas content in galaxies. So y-axis is the surface density of neutral interstellar gas, atomic plus molecular, and they've been normalized so all these galaxies lie on the same scale. Y-axis is radius, and what I want you to notice is that there's this fairly universal profile, except there are these oddballs that have these dips in the center. Our Milky Way is actually one of those oddballs. The Milky Way has a hole in its center. All right, so you see this fairly universal profile of gas and galaxies, except there's some fraction of local galaxies, maybe 10%, that look like the Milky Way and have central holes. All right, now you might say, maybe the Milky Way is just weird, but in fact, this phenomenon of central holiness, pun only partly intended, there's evidence for it at higher redshift. All right, so here's redshift 1 galaxies. And again, we're using specific star formation rate as a proxy here for gas, because gas is really hard to measure at high redshift. All right, and the different colors are just different stellar mass bins. And what you see is, for the lowest mass galaxies, the specific star formation rate is basically the same at all radii within the galaxy. Everywhere the galaxy is doubling its mass at the same rate. It's got the same mass doubling time. But as you go to higher mass galaxies, that's the red line, you see that star formation starts to die off in the center compared to the outside. All right, so these galaxies are forming stars faster at larger radii relative to the stars that are already there than at the center. So the star formation in these galaxies is sort of dying from the inside out. And again, plausibly what's going on is that the gas is going away in an inside-out manner. All right, so what we see that, at least plausibly, is driving the evolution of the velocity dispersion from high redshift to today is gas going away in an inside-out manner. Now, at some level, well, you'd say, all right, well, that's not surprising, right? The gas is turning into stars. It's got to be going away. It's, being turned into stars. The surprising thing is actually how long this takes. All right, so let me illustrate why this is a little surprising. All right, again, x-axis is radius, and y-axis is, all right, so Adam Leroy gets the blame for calling this star formation efficiency, or I don't know, Fabian, maybe that's your fault. This is specific star formation rate. All right, star formation efficiency, it's a thing with units of inverse time. Just think of it as a measure of how quickly the gas is going away. Now, the important line on this plot is this dashed line, and that's where the time it takes to use up the gas equals the Hubble time. And what I want you to notice here is that everywhere inside, say, half of this characteristic galaxy radius R25, the time required to consume the gas is much less than the Hubble time. It's maybe a fifth of the Hubble time. All right, so galaxies, like our Milky Way, should use up their gas in much, much less than the Hubble time. All right, so with that thought in your mind, let me go back and, this is actually a little bit surprising, right? The Milky Way and maybe, one other galaxy in this sample go down in the center and look like their gas is going away. But the time required to use up the gas for all these other galaxies is much less than the Hubble time. Clearly, unless we're living at a special time when every local galaxy is just about to go out, there must be some mass resupply to these galaxies. Mass must be entering not just the galaxy as a whole, but the very center of the galaxy, the inner, fraction of a galactic radius, the inner 25% of the galaxy, in order to keep the star formation going as long as it does. All right, and the required mass supply rate is not small. Here's the distribution of star formation rates in the local universe, and it's a Schechter function. It turns over at like 3 solar masses. All right, so you need to be delivering mass to the centers of most galaxies at a rate of a few solar masses per year in order to avoid having the centers go out. All right, so this is a piece of circumstantial evidence that's going to become very important later on in this talk. All right, there has to be supply of mass to the centers of galaxies in order to explain why they aren't all going out right now. All right, so let me try and, I've thrown a lot of observations at you. Let me just try and summarize the observational situation, because it's going to be important to keep in mind all these constraints as we start talking about theoretical models to try and explain them. All right, so compared to the local universe, galaxies at redshift greater than 0 have higher velocity dispersions and higher gas fraction. All right, they're more turbulent, they've got gas in them. They have the same correlation between star formation rate and velocity dispersion, and the same Toomre Q parameter. That's this parameter that measures how gravitationally stable or unstable a galaxy is. And this Q parameter in all these galaxies is about 1, meaning they're all right at the edge of stability. All right, and this evolution from high redshift to today seems to be mostly driven by a fall in gas content, which occurs inside out, with galaxies emptying themselves of gas in their centers first and only later losing their gas further out. All right, but at a rate that requires that it's not just a matter of gas going away. There has to be a countervailing effect of gas moving into the center. Otherwise, galaxies would go out too quickly compared to what we observe. All right, so that's the picture I want you to all have in your head. Now let's try and explain it. So yes, here's my model that I'm going to use, my spherical cow, although since I do live in Australia, this is the Australian version, is the spherical wombat model. They are actually remarkably spherical if you see them. All right. So what are the ingredients that any model like this should have? Well, all right, here's some basic ones. Star formation seems to be important in all of this. Stars have this habit of blowing up as supernovae that might be important for driving turbulence. All right, so our model should include star formation, and we'll parameterize it super simply. We'll say that the star formation rate per unit area is equal to the gas mass per unit area. That's what this sigma is. All right, natural time scale is what's called the free fall time. That's just how quickly gas would collapse if nothing were stopping it, if gravity were the only important force. All right, and then we'll have this parameter epsilon ff, which is just how much slower things are than that due to whatever. Not going to worry about what that whatever is in this talk. I'm just going to say it's a parameter. All right, and the free fall time you can calculate in terms of the density of gas. That's this rho. Just depends on the density of the gas. All right, vertical force balance. It's probably good if our model, respects momentum conservation. All right, and force balance is just another form of momentum conservation in steady state. So we want it to be the case that our model does not predict that all galaxy disks are about to explode or that they're about to collapse down to pancakes. We want there to be a balance between gravity, which is trying to pancake them, and pressure, which is trying to blow them up. So we will equate the order of magnitude level. This is the dynamical pressure in the interstellar medium, the density times the velocity dispersion squared. All right, and this is the pressure due to gravity. It's just gas surface density times total surface density times g. All right, here's this two-ray stability parameter I talked about before. Galaxies seem to know about it. Our model should too. All right, and it depends on this omega is the angular velocity of the galactic rotation. This sigma is the velocity dispersion again, and then we divide by g times the gas times the total surface density. All right, so we've got momentum balance. We should probably have energy balance. All right, and this is where the key to the model is going to come in. All right, our model should conserve not just momentum, it should conserve energy. And in the interstellar medium, what are the energy inputs and outputs? All right, well, the main energy loss mechanism is that when I've got this gas moving around at the sound speed, or twice the sound speed, or in the case of a high redshift galaxy, 30 times the sound speed or something, it's inevitably going to shock against itself. Gas that is moving around supersonically is going to have shocks. And in the interstellar medium, those shocks are radiative. All right, so the gas is going to pancake, it's going to heat up, but the density is really low, and so all of that heat is immediately going to be radiated away in the form of photons, which will escape the galaxy. All right, so that's an energy loss mechanism. As the gas runs into itself, it will shock, heat up, emit photons, and cool back down. All right, and we know from numerous simulations and studies at about what rate that happens. The energy dissipation rate is of order. All right, this is the energy per unit area, and we divide that by the crossing time of the largest eddies, and the largest eddies in a galaxy are comparable to the size of the galaxy disk itself, the scale height. So that's h, and then we divide by the velocity dispersion to get the crossing time, and we have an expression for the turbulent dissipation rate. I'm leaving out factors of order unity here. They're in the paper, but I'm not going to stick a bunch of factors of order unity on the screen. I have too many equations as is. So that's the turbulent dissipation rate. So that's the loss term. What about the gain term? All right, well, the most obvious mechanism to put energy into the interstellar medium is that these bombs keep going off in it. All right, we have interstellar gas, and it likes to collapse and form stars, and some of those stars are massive, and those massive stars then insist on blowing up at the end of their lives. And if you set off a bunch of bombs in something, that tends to make it turbulent. So at what rate do all those bombs inject energy into the interstellar medium? All right, well, I could sort of give almost an entire talk on this. I'm simply going to assert that the result is the following. All right, well, first of all, we have the rate at which the stars that are going to explode form. It better be proportional to that. If I form twice as many stars, I will eventually, down the road, have twice as many supernovae blowing up. So I've got that term. All right, and then I have to have this P over m star, and this is a critical object. This is the asymptotic supernova momentum. All right, so what is that? Well, when these bombs blow up, they start expanding into the interstellar medium. And initially, they've got a ton of energy. All right, each one of those bombs injects 10 to the 51 ergs of energy. But that doesn't all wind up in motion of the gas. Most of it goes into heating up a little bit of gas, which as it expands, does work on the gas around it, but also radiatively cools. And eventually, that hot gas radiates away all its energy, and what's left is an outward moving shell that's just coasting from the initial push. And that outward moving shell has a certain amount of momentum it carries. All right, that's what this asymptotic supernova momentum is. It's the momentum carried by this outward going shell And I've normalized it so it's not per supernova, it's per total mass of stars formed. So I'm here accounting for all of the stars that don't blow up. All right, I only get about 1 supernova per 100 solar masses worth of stars that form. That 1 supernova, it turns out this asymptotic momentum is about 3 times 10 to the 5th kilometers per second times solar masses. You get 1 per 100 solar masses, so this is the asymptotic momentum. And that's the mechanism that's going to stir up the interstellar medium, is these asymptotically outward moving shells of matter that have been flung outward by the explosion. And the rate at which those shells will deliver energy is of order the rate at which they go off times the momentum per explosion, or the momentum per unit mass of stars formed, times the current velocity dispersion in the ISM. That's the rate at which energy will be injected. All right, so if I just put these terms together with these ones up here, I can write out the gain and loss terms in terms of now my other variables. All right, now this is very interesting to notice. Notice that almost everything here is the same. These two things are almost the same. The only difference here is the cube here and the square here. That's going to become important in a moment. All right, so I've done the hard part, I've done the math. Now let's do something conceptual. All right, so let's try and make a model putting all these ingredients together. So here's our first and simplest one. All right, my model is vertical balance in the ISM will set the density in the ISM. And that density will determine, if I know this epsilon FF parameter, the star formation rate. That star formation rate will determine the amount of feedback, the rate at which supernovae blow up. That feedback will set the amount of turbulence, balancing energy injection and energy dissipation. And that turbulence is what maintains the vertical balance. All right, so I have a complete story for how this all works. All right, so what's epsilon FF? I'm just going to take that from observations. It turns out that observations say it's about 1%. All right, here's a plot of measured epsilon FF values. Again, I could give an entire colloquium about this. I'm just going to assert that this is what the observations say. If anyone wants to argue with me, do so later. Epsilon FF is about 1%. All right, so here's our gain rate, here's our loss rate. I set these two equal and I can solve, and the only thing that doesn't cancel out is this sigma. And I get that this sigma is epsilon FF times this asymptotic momentum. And lo and behold, I put in this order 1,000 kilometers a second. I multiply it by a number of order 1%, again, leaving out the factors of order unity, and I get like 10 kilometers a second. That's a remarkable result. All right, from nothing more than elementary considerations of energy balance, the properties of supernovae, this asymptotic momentum, and this observed epsilon FF, I explained that plateau. Why do all galaxies have 10 kilometer a second velocity dispersions in the local universe? This is why. So that's great. And you can in fact test it with simulations. So here's a simulation done by, series of simulations done by Ryan Zhang, where they just took idealized interstellar media and set off supernovae in them, and they scaled both the supernova rate and the gas content following just the observed correlation between gas content and star formation rate. And lo and behold, they always get about 10 kilometers a second as the equilibrium velocity dispersion. So that's great, but of course there are problems. Some galaxies have larger velocity dispersions than that. We haven't explained them from this story. All right, and more conceptually, what happens if 10 kilometers a second isn't enough for your galaxy to be stable against self-gravity? And what I mean by that is, we know that these high redshift galaxies have tons of gas in them. They've got very, very high gas content. All right, and the higher the gas content, the higher a velocity dispersion you're going to need to keep Q at 1. All right, if I make this sigma big, I'd better make this sigma big if I want Q to be 1. This model doesn't explain what happens if I've got so much gas in a galaxy that just supernovae can't maintain Q equals 1. All right, so what do I do next? So here's an alternative story. An alternative story is I say, well, all right, if Q equals 1 is an important thing, maybe I should try and put it into my story. And the way I'll put it in is I'll say, well, all right, I'm going to demand that my galaxy be gravitationally marginally stable. I'm going to assume that if it isn't, that self-gravity will make the gas start to clump up, it'll become turbulent, mass will move down the potential well, that will increase the velocity dispersion, and I'm going to demand energy balance that way. So gravitational instability will set the rate at which mass moves down the potential well, which determines the rate at which gravitational potential energy is released. That gravitational potential energy will eventually be dissipated as heat and radiation, but on the way, it has to take the form of turbulence. And that turbulence is what I'm interested in. All right, so just to sort of show you that this isn't a crazy idea, here's a simulation done by Nathan Goldbaum, all right, of a galaxy that we just set up in smooth state, let it run for a while. All right, and we let it run until it reaches statistical steady state. All right, after a while, you see it settles down, it forgets its initial conditions, it looks kind of pretty. All right, and you can ask, well, all right, if my story is that the velocity dispersion here is being maintained by gravitational instability, well, the power's got to come from somewhere. Where it has to come from is mass moving down the potential well. That's my source of available energy. Is mass moving inward? And the answer is, lo and behold, yes, it is. There is a net inflow rate in this simulation, which in fact matches the star formation rate. All right, so mass flows down the potential well, and that drives turbulence. Yes, question?
Why don't you form a bar in this case?
Because our initial conditions have a bulge, so it's stable in the center. It's possible if we ran it long enough, eventually that bulge would form a bar, but it's pretty hot in the center, so it doesn't form one within the 600 megayears we ran the simulation. All right, in fact, there's direct evidence that this process is going on too. You can directly measure in nearby galaxies that there is mass flowing inward. Here's some work from Schmidt et al. All right, in this galaxy NGC some telephone number, and you can measure that there is a net inward radial mass flux of order of solar mass per year. All right, so mass flows down the potential well. Let's try and make a theory from that. All right, so my theory is there's energy released by gravitational transport. So I dig out my copy of like Frank King and Rain or whatever textbook you learned about accretion disks from. All right, and I say when mass moves inward in an accretion disk, how much energy gets released, and this is the expression for the energy released per unit area. All right, so I set that equal to the dissipation rate instead of anything to do with star formation, and I solve and I get that there's a net mass inflow rate. All right, so I can work out a model for a galaxy disk where inflow of mass balances dissipation, and I can work out what the star formation rate in such a disk would be. All right, and I get these lines. All right, these different colors here are for just different parameters. One, the blue is parameters appropriate to a local dwarf, so that's a rotation speed of about 100 kilometers a second. A local spiral is more like a 200 kilometer rotation speed. A ULERG is higher, a high redshift galaxy. And it nicely covers where the data are, but you see it misses terribly here. It doesn't get the floor right. All right, and that's because galaxies down here would be perfectly gravitationally stable. They've just got very little gas in them. They don't form many stars. All right, so let's try and put those two things together. All right, I mean, right, there's no law of physics that says only star formation can drive turbulence or only gravity can drive turbulence. Both processes exist in nature. Being a theorist, I am capable of using a plus sign. All right, so I put those two together, and then I solve. And it turns out that what you can solve for here naturally is the rate at which mass flows through the galaxy. All right, this is the rate at which mass flows through the galaxy. All right, depends on the velocity dispersion. And then this factor here. And what's this factor? Sigma SF is this 10 kilometers a second floor set by star formation feedback. All right, so there's a very, very simple interpretation of this. There is a minimum, there's a velocity dispersion of about 10 kilometers a second your galaxy can't go below. That is imposed by supernovae blowing up. No way to avoid it. But if that is not enough to maintain Q equals 1, then your galaxy will compensate by additionally having some mass flow toward the center of the galaxy, which will pump up the velocity dispersion further. And the fraction of the energy that's coming from star formation is this sigma SF over its total sigma. All right, so that's where the energy comes from. And if you put those two together, you can actually match the observations pretty well. All right, now, this is, I'd say, reasonably impressive by itself, but in fact, you can also match a bunch of secondary dependencies. All right, so in addition to this sort of mean velocity dispersion as a function of star formation rate predicted by the model, there are secondary dependencies in the model which I haven't worked out for you here in the talk, but which are worked out in the paper, on the galaxy rotation curve and the velocity dispersion. All right, and you can check these against the observations. All right, and so here's some work from Ubler et al. Showing that, all right, so the models are just, the lines there are just models with different galaxy rotation curves. From dark is a high-speed galaxy to lighter is a low-speed galaxy. And the points are observations, again colored by the rotation speed of the galaxy. And the thing to notice here is the dark points all live on the right side of this diagram, and the light points all live on the left side of the diagram. All right, exactly what the model predicted would happen. All right, so that works pretty well. And I just want to emphasize, this is an actual prediction, not a postdiction. This is a prediction. All right, Ubler et al. Took our published model and plotted it against their data, which was after our model came out. All right, you can also check against the gas fraction, but I'm short on time, so I'm going to skip that. Instead, I'm going to go on to where this model falls apart. All right, so this model, I think, works pretty well. Where does it not work? All right, and one place where it clearly doesn't work is in the center of our galaxy, the central molecular zone. All right, so let me just start with an orientation. All right, Diedrich, Melanie, you can go to sleep for this part of the talk. For those of you who do not think about the central part of our galaxy that often, let me just orient you to what's going on there. All right, we have this sort of ring of gas in the center of the galaxy. The exact geometry is not totally clear. All right, here are a bunch of proposals: spiral arms, an elliptical orbit, an open stream. Here's sort of Diedrich's model for what the gas is doing. All right, the point is all the gas in the center of our galaxy is collected in this sort of ring-like structure. That's where all the dense gas is. Further out, there's lower density gas. All right, and this ring-like structure has high velocity dispersions. All right, now, the way this gas forms stars is a little weird. If you look at the Milky Way and other galaxies, you find a big diversity of what goes on in the centers of galaxies. Some form stars faster than the rest of the galaxy. Some form stars the same rate as the rest of the galaxy. Some form stars slower. All right, so we've got this big diversity in how quickly galaxy centers form stars. All right, and that's suggestive of time variability. There's a high velocity dispersion, but there's a low gas surface density. All right, which are things that shouldn't go together in this model. All right, the model says Q should be about 1. Galaxy centers don't have Q of 1. All right, so what's going on here? All right, and the answer is gravitational instability can't be responsible for moving the gas into this ring, because Q is much bigger than 1. It can't be responsible for driving turbulence. Instead, there must be some other mechanism that's injecting energy. And it has to operate in nuclear regions. All right, and a proposal that Diedrich and I made a few years ago is that the energy source here isn't the self-gravity of the gas, it's the gravitational interaction between the gas and the stars. All right, because, and this is where bars come in, the potential in the center of our galaxy and many other galaxies is not axisymmetric. There's a stellar bar. So you've got this non-axisymmetric potential, and when the gas tries to orbit within this non-axisymmetric potential, it gets perturbed. And it turns out there's an instability if you're inside what's called the inner Lindblad resonance of this non-axisymmetric potential. If you're trying to orbit inside the inner Lindblad resonance of this potential, there is an instability where every time the gas goes around, it gets kicked by the bar in the same direction, waves build up, and the gas becomes unstable. All right, now, the nice thing about this instability is that it depends on the amount of shear in the rotation. The instability only occurs where there's shear, and inevitably in the center of a galaxy, the shear has to turn off somewhere. The velocity shear can't go all the way into the center because then you'd have an infinite gradient at the center. Eventually, the rotation curve has to turn over from flat with high shear to more like solid body with low shear. All right, and in our galaxy, that turnover occurs at about 100 parsecs from the center. That's this red line is the amount of shear. The blue line is an estimate of the rotation curve. And this instability, its growth rate, gets slow when you go into this low shear region. Now the nice thing is this low shear region is exactly where this ring lives. All right, so we can make a simple 1D simulation of how this works. All right, so here's a simple sort of 1D disk model where gas flows in from the outside and then it hits this low shear region and it gets stuck there. All right, where it gets stuck, the velocity dispersion plummets and the star formation rate rises. So you only form stars in this ring. And you wind up with this very bursty star formation behavior. All right, now that's a 1D model. Here, let me show you some 3D simulations. So this is work by Lucia Armolata, who's a former postdoc in my group. All right, just showing a simulation. That gray circle there is just sort of to give you a sense of where the ring is. All right, now you see that the bar makes the flow highly non-axisymmetric, but eventually, after a while, we accumulate gas in a ring about where it's observed to be. We don't get the location exactly right, but it's in the right neighborhood. All right, so this story seems to hold together. All right, we wind up with this nice ring. And we get, for free, automatically out of this simulation, that the star formation is highly bursty. All right, so here's the star formation rate in the simulation. And you see it varies by orders of magnitude as required by the observations. All right, and in fact, the current Milky Way central star formation rate is down here. We're probably near a minimum of the cycle of star formation in the Milky Way right now. All right, I think in the interest of time, I'm going to skip through the extragalactic comparison and just go to the end. Read the captions. It's worth reading the captions. I put them in there so you don't all look like this at the end of the talk. All right, so where are we? So I think there's been some progress towards explaining the origin of turbulence in the ISM. In particular, it's possible now to make a model and put together star formation feedback, turbulence, the velocity dispersion, and fueling of galaxies, the transport of gas through galaxies, into a sort of single coherent framework where everything sort of hangs together. All right, it explains the origin of turbulence in the interstellar medium and explains why that turbulence is correlated with the star formation rate in the way we observe. It explains why there's this plateau of 10 kilometer per second velocity dispersion in low star formation rate galaxies and why it goes up in high star formation rate galaxies. For free, at the same time, it solves the problem of fueling star formation over cosmic time. It explains how gas gets to the centers of galaxies. It gets to the centers of galaxies because it's being driven there by the need to maintain marginal gravitational stability, which causes mass to flow inward to maintain the velocity dispersion. All right, now, this works fine, except when we get to the very centers of galaxies, where the gas is almost all gone. All right, and there the dynamics changes, and the big change is that bars become dynamically dominant. All right, there's another energy source that we have to think about, and that energy source is the interaction of the non-axisymmetric stellar potential with the gas. That's not dominant out where we are, but it is dominant within the central few kiloparsecs of the Milky Way. All right, now, what haven't we done here? Problems. All right, well, one is a critical ingredient to this model was this epsilon FF, which I simply took from observations. All right, this is the sort of microphysical relationship between the amount of gas and the star formation rate. And we observed that it's about 1% of the mass goes into stars per free fall time. That's what we observe. Why is that? That is an excellent question, which this theory does not at all answer. All right, so this is an input to the theory, not an output. Ideally, we'd like to be able to explain where this comes from. Now, I've worked a lot on where this comes from, but in this particular talk and for this particular model, it is very much an input, not an output. The second problem. Can we understand the transition between the normal regions of a galaxy, where this sort of model of self-gravity and feedback applies, and the regions like the center of the Milky Way, where all of a sudden we need to start worrying about stellar dynamics taking over and running the show? These gas-depleted regions where the bar is the dominant source of energy input. All right, there seems to be a transition between the two. In the Milky Way, it's at sort of 3 kiloparsecs. Can we have a more general understanding of how bars work in this model and where and when they're going to become dominant? All right, and finally, a problem for the observers is, all right, there's very clear predictions in this model about inflow rates and their properties in different galaxies. All right, now I showed you like one measurement of an inflow rate, and I believe in the Schmidt paper there are what, like 4 or 5 galaxies. It's not a big sample. Ideally, it would be nice to be able to measure inflow rates in a range of galaxies and be able to see what's going on not just in the nearest, most local spirals, but in other galaxies as well. That's what we'd like to be able to do. And if we could do that, then you could actually test this model more, because there are very strong predictions about the relationship between inflow rate and galaxy properties. But I will leave that as work for the future and end up here. Thank you.
Thank you, Mark, for a very exciting talk. I already see several questions, so I'll just walk up here and start.
Thank you. Can galaxy-galaxy interactions affect star formation?
So can galaxy-galaxy interactions affect star formation? Yes, certainly. All right, so, I mean, obviously, if I take 2 galaxies and I smash them together, that's going to completely transform everything. So this is very much an equilibrium model. It does not apply when 2 galaxies are in the process of smashing together. Now, the good news from my perspective is that galaxies smashing together is a relatively rare event, and very few stars are formed in the course of such collisions when you average over cosmological timescales. Most stars form in a quiescent mode, and after a collision, galaxies settle back into equilibrium pretty quickly. Once there's a collision, they sort of settle down after 1, maybe 2 orbits. All right, and the time between large collisions is much longer than that. All right, so this model does not apply during a collision. Collisions are averaged over cosmology relatively unimportant.
First, thank you very much for the talk. Without going all the way to mergers or like smashing collisions like that.
Sorry,
without going to the merger case or something like that,
yeah.
One difference between high and low redshift is the cosmological accretion. So I wonder, like, where does this energy input comes in your model?
Yeah, so cosmological accretion is clearly a big difference between high and low redshift. And I mean, what I would say is cosmological accretion is the reason there's so much gas in the high redshift galaxies. All right, so it's providing the fuel that makes this entire process go. I didn't talk about it in the talk, but you can sort of turn things around. You can say, all right, well, if I average over times comparable to like gigayears, then really what should happen is the equilibrium into which a galaxy settles will ultimately be dictated by the rate at which mass is supplied by cosmological accretion. Now, most of the energy that's available from that cosmological accretion isn't in the initial fall of the gas onto the galaxy. All right, because the gas falls on mostly at large radii, and when it falls on, it tends to shock and lose most of its energy. So the energy is not in the initial infall. The energy is when the gas then flows inward through the disk of the galaxy. All right, and it's very much like, I mean, if you think about like accretion onto a compact object, right? If you're falling onto a compact object, half the energy comes out between R star and 2R star. Now, it's not quite as extreme for a galaxy, but it is still the case that most of the available energy is as the mass flows through the disk, not when it first joins the disk. All right, so the main role of cosmological accretion is to supply the fuel that will flow through the disk.
So you nicely explain the, let's say, the turbulence, yeah, in this model on the larger scales, let's say kiloparsec or something like that, or thickness of the disk.
Yes.
Can you, yeah, and it depends on matter inflow, because you need to get mass for the star formation for a long time, and the supernova explosions are heating, or
that's one source of energy.
So yes. Can you say anything about the smaller scales, how it is cascading down or up? Because you know the old Larsen relations from the 80s, yeah, that we have a correlation between velocity dispersion and scale.
Yes.
And there the idea was that on larger scales the energy is introduced, yeah, and then it's cascading down before it's radiated away.
Yeah.
Now, can you say anything about this image?
Yes, I mean, my picture would be that the Larsen relation is basically telling you about just the normalization of the total amount of power in the interstellar medium. So yes, as you go to smaller scales, there's less and less energy. This is what's expected for both subsonic and supersonic turbulence, just with slightly different exponents. All right, so what is supplying the turbulence that you're seeing with the Larsen relation is ultimately this process, just cascading down to smaller scales. All right, so the Larsen relation, the normalization of the Larsen relation is telling you about the velocity dispersion of the ISM as a whole. All right, if you take the sort of Larson relation and you extrapolate it up to the thickness of the Milky Way disk, you will get 7 kilometers a second, roughly, which is indeed the velocity dispersion of the ISM in the Milky Way as a whole. All right, so I'd say the Larson relation is basically just giving you data points at different length scales in the turbulent cascade, of which this is the outer scale, and where the ultimate power source is some combination of supernovae and gravitational instability from mass inflow. In the Milky Way, we're at about 50-50.
So amazing that all of this falls out from such beautiful first principles. I was curious, since it's more or less a closed box model, how, and we know that at least at high redshift, outflow mass loadings had to be order unity or more. Have you put any ideas as to how you would adapt this when a significant amount of your energy and momentum from supernova are actually leaving the disk to power the outflows that we need to remove mass and metals?
Yeah, so I mean, within the context of this model, I mean, I can give you this sort of the lame answer. The lame answer is within the context of this model, all of that is hidden inside, you know, a P over M star. Right, that's all right here. All right, so if you say that my outflows are super bubbles that are blowing out and, you know, so a lot of the energy gets lost, then maybe this number changes. All right, that's how it would sort of show up in the model. Now, that's one side. On the other side, and I mean, I had this, I didn't mention it, but it's, you know, it's down at the bottom there. Clustering potentially makes this number bigger. All right, so you can certainly worry about whether this number should be, you know, a factor of 2 smaller because some of the energy is being lost to outflows, or a factor of 2 bigger because stars are clustered and therefore their terminal momentum makes this energy input bigger, or it makes the momentum input bigger. Honestly, I would not call the factor of 2 uncertainty on this the biggest uncertainty in this model. So that's sort of how I would have it show up in the model.
Mark, there is a large subset of galaxies that don't form stars by any appreciable amount. Your model, I presume, is not applicable there, but what aspect of the model is not applicable to red and dead galaxies? Is it just the black hole as a different feedback, or is it the gas supply?
Yeah. So I'd say it's the gas supply and the gas content, and the thermal state that implies. All right, so sort of an implicit assumption in this model is that the gas is sort of disky and not thermally supported. All right, if you're in a galaxy where the ISM is mostly not neutral, right? If you go to some elliptical, some, you know, giant central elliptical where there is interstellar gas, but it's all up at 1,000,000 Kelvin or something like that, then thermal pressure is running the show. All right, now if you go to something that does have a neutral interstellar medium, all right, so for example, you go to some of the S-zeros, but ones that still have, say, H1 or molecular gas, like the sort that, you know, say Martin Bureau has studied, or Katie Alatalo, or Tim Davis, those are interesting, and I would say in those models, those are probably much more like the galactic center in that those are not a Q of 1. All right, gravitational instability is probably not an important mechanism for that gas, it's just nowhere near being unstable. All right, now what the energy input is that stops all that stuff from turning into stars, I don't know. But this model is sort of intended to aim at galaxies where Q is about 1, and those galaxies are not in that category.
So to get gas to flow radially inwards in the disk, you obviously need to transfer angular momentum outwards. So
Yeah.
what's the mechanism? Is that just gravitational instability everywhere? Or?
Yeah, well, I mean, it's torques driven by the non-axis symmetry of the gas. So, I mean, again, we don't, you know, I didn't show it in the talk, but you can directly measure in simulations like the one I showed the torques. And there's both a Reynolds stress and a gravitational stress, all right, coming from the fact that the ISM is highly clumpy. And that stress gives you a mechanism to exert torques that move angular momentum outward.
And does that give you enough inflow to explain the star formation rates?
Yes, it does. I mean, so I showed you one example where, I mean, the gas inflow rate sort of matches the star formation rate. Now, depending on the exact parameters you put in, it may not supply all of the star formation rate. So I had another simulation I didn't show where the gas inflow rate was enough to supply order half the star formation rate. All right, but you can certainly find places in parameter space where inflow is sufficient to supply all of the star formation and keep you in steady state, as long as, of course, you've got gas on the outside that you can bring in. If you run out of that, you're done.
So we already had a discussion of the supernovae feedback recipe, and I mean, you have it on your slide that a possible solution could be that this value is larger, and then you said, well, it's just a factor of 2. Could you elaborate on that a little bit? Because, I mean, the clustering effect of star formation may actually impact this recipe quite a lot, I thought.
Well, okay, so I mean, that's sort of what this Gentry paper is about. I mean, or these Gentry papers. So, I mean, you can, all right. The amount of boost to the momentum you get from clustering, I would say, is still extremely uncertain. And the reason it's extremely uncertain is you can basically do 2 limiting cases. You can do 1D simulations where there's no mixing between the hot gas and the cold gas, where you have a perfectly smooth interface between the two. And then you get a certain boost. All right, and it turns out it can be as much as a factor of 10 for 10 supernovae. That turns out to be the optimal number, is 10 supernovae. All right, you can also do a case of, all right, let me do a full 3D simulation where I get all the instabilities right, but it turns out the biggest simulation you can afford, the mixing between the hot and the cold gas is still completely dominated by numerical mixing. And the simulations don't converge at least the resolutions that we can afford. All right, so you can get lower and upper limits on how much of a boost factor you can get. All right, but here's the good news from the perspective of this model. Even if you take the upper limit case, I said you can get a factor of 10 boost in this number for 10 supernovae. All right, but not all stars form in clusters of exactly 10. All right, they form in a range of cluster sizes. And so you can measure what this boost factor is in the 1D simulations. Right, the nice thing about 1D simulations is you can run lots of them, they're cheap. And you can run them for many, many different cluster sizes, and then you can integrate over the cluster size distribution that we observe. And it turns out that when you do that, you get at most a factor of 2 boost. All right, so even if you take the upper limit, averaged over all clusters, you get only a factor of 2 here. Now, for an individual cluster, it can be a much bigger effect. So like 10 supernovae clusters, this number becomes 310 to the 4 instead of 310 to the 3. But that's sort of at the most efficient size scale.
I have a question, actually.
All right.
I promise it's not about the final part of the talk. I suppose if I look at the questions that we just had, one thing that people are interested in is, okay, how does this change if you go away from the main sequence? I envision that if you take results from recent sort of turbulent star formation models, that the epsilon FF, so the efficiency per free-fall time, depends to some extent on the virial state of the gas. So if the gas is highly supervirial, it forms stars less quickly. Yes. Now, of course, the virial parameter, at least conceptually, is related to something like tumor Q.
Yes.
So could you insert something like a model where your epsilon FF actually depends on tumor Q, and would that increase the applicability of this model to quenched systems?
Yeah, so yes, in principle you could, and that's a good idea. I think Phil Hopkins' model, he tries to do something sort of like that. I think in detail it doesn't work very well against the observations when you try and look for the correlations with Q. But I agree that in principle you could say, all right, well maybe if Q is really big, epsilon FF should go down, and then you could extend the model to galaxies that are not at Q of 1. That's an interesting idea that might be worth exploring.
And then finally, we talked a bit about major mergers earlier, but of course galaxies, especially on the main sequence, are still accreting minor galaxies, dwarf galaxies all the time. That could probably drive talks as well. So what happens if you basically add an additional external inflow term on top of your current model? Would that basically drive up the turbulence further? Because I expect that if you have high M stars, so high star formation rate, you basically end up looking at galaxies that also have a larger number of minor mergers, and therefore you would get more
so I mean,
transport.
if we look at this equation, right, so if you look at what would happen, if you have extra external torques, this transport term goes up, and then your equilibrium velocity dispersion goes up. Now, it's not a huge effect because this dissipation rate has a sigma cubed in it, so you need a lot of external accretion driven by external torques to move this by much, right? Even if you increase the transport rate by a factor of 10, this is only going to change by a factor of 2.
Good. Are there any further questions? Sorry, I can't actually see if I stand in front of the... Okay. Then before we thank Mark again, 2 practical announcements. First is we're going immediately after the colloquium for drinks with Mark and then dinner at Mughal Tandoori. That's the Indian restaurant here right close to the bridge. If you would like to join, please come talk to me down here, and Ben Keller, thank you Ben, is organizing the dinner, so please talk to either Ben or me immediately afterwards. Then next week, I see that he actually just left, but next week we have a colloquium by our own Frits Rupke about the 3D view on stellar astrophysics using very high resolution simulations compared to the ones we saw today. So I look forward to seeing many of you again next week. And for now, let us thank Mark again for a really wonderful talk. As I said, he is going to be around for the next 6 months. So thank you, Mark.